Ed, if I'm going to find the derivative of my sine function, d dx of sine of x, that's telling me that my function f of x is equal to sine of x. We're going to use the traditional limit definition in order to discover this, the one with h. Limit as h approaches 0 of f of x plus h minus f of x all over h. I only go back to this formula because I can't remember or I can't figure out how to do it with the alternate one, which is a nicer formula to work with. I tried figuring it out on the drive in this morning, but there's something missing. I think it involves conjugates, but I need some time to figure it out. So possibly tomorrow. So for now, we're going to say the sine of x plus h minus the sine of x all over h. And I don't want to look it up. That's the thing. Like that's where my personal pride comes into play. I want to figure it out. I don't want to cheat. All right. So then you get to this step, and you might stare at it for like half an hour trying to figure out, oh wait, can I factor something? Can I cancel the h's or something like that? It isn't until you realize that there is an identity for this. That's when you could take the next step. So it's the limit as h approaches 0. This becomes sine x, sine a, wrong function, cosine h plus cosine x sine h. All right, so that's the sum identity for sine x over h. All right. Once you get to this step, then it becomes algebraic manipulation that'll get you the rest of the way. And but that's where we're going to leave it. We'll pick up with this tomorrow after we go over the homework. And we were kind of making some headway. Then the bell rang. So we lost our mojo, lost the groove. I'll show you the other way to do the method involving the alternate limit definition. I mentioned yesterday that I haven't quite figured it out, but as so often happens, the minute you guys walked out of the room, I was like, oh, maybe I should try that, and then of course it worked. So I'll show you how that looks. You may not like it though, not because it's hard, but because it's not really universal. Anyway, so we use the traditional limit definition. We expanded sine of x plus h using the sum identity for sines. Now we're at the point where we need to try to clean it up. The cleaning up process comes from regrouping so that we can simplify. Simplifying meaning get a common factor, if that's possible, or any kind of factoring. I already used purple. I'll go black here. So I'm going to put these two together. So we're looking at, let me just put this over here. Limit as h approaches 0 of sine x cosine h minus sine of x. I'm going to put that, I'm going to make it its own fraction, over h plus cosine x sine h over h. All right. Maybe you see where it's going, maybe not. This limit is related to the variable h. So anything that doesn't have an h in it really doesn't need to be there. So I'm going to split it. I'm going to actually show every step in detail, but just know that we can streamline this greatly. But I want to make sure that I show it at least the first time explicitly. So I'm going to write the limit of each of those two fractions separately first. Bless. I didn't do the worst form of cheating, though. The worst form of cheating is when you have version A of a test and you copy down the answers to version B, because that's what the kid next to you has. That's the worst.
Someone did that to me bio.
That's awesome.
It was so funny.
It's so satisfying.
How many times does that happen?
What's that?
How many times does that happen? That happened kind of a lot.
That happened like last week. Again. But you know what? I think as a teacher, it's not like I'm encouraging it, but when I see it happening, I'll make the standard comment of eyes on your own papers, folks. It's not going to end well for you, things like that. But I don't like call people out for it because I already know how the story ends. So part of me does sit back and kind of enjoy it, but it is sad for the individual. Yeah, not because they're going to get a bad grade, but just because they're not like with it enough to know that their work doesn't even remotely correspond to the question. Like, you don't even have enough of a sense of the math to know that that doesn't belong with that problem. Yeah, that's the sad part. So I broke off the sign of x from the rest of the fraction, the part that has all the h's in it, because the x stuff doesn't need to be there. I'm going to pull it out of the entire limit.
The last part you can simplify, right?
Yeah, big time. What does this limit become? I think I heard it. 0. This one becomes 1. Okay. 0, 1. And so we end up with cosine of x as the derivative. Let's see what kind of notation I use, just d dx. Okay, so let me just write that. D dx of sinus of x. All right, so it does clean up kind of nice. Yeah. All right, so let me show you the other way to do it. It's, at least in the early goings, it looks like it would be an easier way, but then there's a little bit of a twist that makes it kind of interesting. Definition. And then we'll see if we can start to streamline this a little bit. So it's going to be the limit as h approaches 0, cosine x plus h minus cosine x all over h. First step shouldn't be too bad. Second step shouldn't be too bad either, because that's where we're substituting in our sum identity for cosine. Right? So cosine a plus or minus b is equal to cosine a cosine b minus plus sine a sine b. Miss Ingram has a mnemonic for remembering those. It involves a song, singing a song. I'm not big on that kind of stuff. I know it's the song Changes by Bowie, yeah. I don't know what the mnemonic is, so I really can't do it. Yeah, I don't know. So maybe next time she comes in, I'll have her do it for you, or you can just kind of find her somewhere. Tell her to sing it to you. It'll be weird, but she'll do it. So, expand it out. Trying to get kind of a consistent color scheme here. All right, so then it becomes a matter of just reorganizing, simplifying, and finding rules that apply. So the cosine x's would go together. You don't have to do it the way I did it the first time, which is to show every tiny little detail. There's some things that you can assume. So like, for example, instead of breaking this apart, I can just identify the sine h over h part and make that go to 1. It's a little trickier when it comes to the cosine one, because how do you really illustrate the cosine h minus 1 over h without doing the factoring? I mean, if you want, though, I've seen people do this before, and I'll accept it. Just kind of tuck it off on the side, or on the top here. Cosine x cosine h minus 1. And then somehow make it clear, I won't highlight, I'll just go with this. Make it clear that these two are going to 0. I don't know, I'm just trying to save you a little work. All right, so, and I'll even strike through the blue there just to make it really clear. All right, so this expression got replaced with that one. This piece in conjunction with the h goes to 0, so we know that that whole shebang is canceling out to 0. You got to show me something. You just don't have to go too crazy. What I don't want to see is, you know, the blue expression here unaltered with a strike through saying 0. Like that's kind of, I mean, it's not cheating, but it's, you're not. Well, yeah, but it's disingenuous, because what you're doing is you're using the fact that you know that the derivative is supposed to be negative sign because you memorized that, figuring that this has to go to 0 in order for it to work out. You have no idea why. You just know that it has to happen, so you're just going, okay, 0. So you're missing the part where you're demonstrating the knowledge and skill. All right, so, and then I'll be missing the part where I give you full credit. So, you compare the work. I mean, I exaggerated the steps when I did the sign, explained everything, reorganized, showed every little detail, and it took a while, took a lot of space. But then when I streamlined it and wrote it smaller, obviously, I don't know why I wrote it smaller, but I wrote it smaller, and it doesn't take as much space. All right. The purpose behind this is for us to learn where the shortcut rules are coming from. That's what I've been mentioning repeatedly. It's not for us to, I mean, we should be honing our skills on using the limit definition, but not, you know, in and of itself. That's not the end of the road. That's just a tool or a resource to get us to understand where and why the shortcuts are working and how they're working, right? So yeah, it's kind of a necessary evil at this point. I know when I was a student, it was like, enough of this limit crap, let's get to the derivatives. And then once we got to the derivatives, it was like, all right, this is getting hard. can we go back to that limit stuff? You know, it's hit or miss. Oh. I don't know if anybody got this, but somebody can have it. Hey, why is that like that? It's
It
like-
is why.
No, I just said that there wasn't enough room to answer the question.
Mr. Gantz, how do you know what to use the x plus h minus f of x1 or the f of x minus f of a over x minus a?
So what we're getting at is the idea that it seems like the f of x minus f of a one is a really good, useful one for almost everything except for trig. Once you get to trig, you want to kick over to this one. All right, so again, the point behind this is to kind of work off of what we just figured out. So we learned about a constant multiple rule that tells us that we can think of a function, if it's got a constant multiple, as the multiplier separate from whatever the main function is. All right, and then take the derivative of the main function, the parent function. It's kind of, there was a reason behind all that talk of parenting and siblings and ancestors and descendants. The derivative of cosine is negative sine. It took way too long considering we literally just figured it out. So negative sine of x. So pi times negative sine of x would be negative pi sine x. What's my h prime going to be? That one's even easier.
1 minus cosine.
1 minus
Plus.
plus cosine of x. All right. The sum rule for derivatives tells us that we can take the derivative of each part separately. Derivative of a linear function is just the slope of the whatever the line is. The derivative of sine we just discovered is equal to cosine. All right. So these were, prior to the instruction on how to get the derivatives of sine and cosine, these were a lot more challenging than they ended up being. I'm going to rewrite this one as 2 times x to what power? Negative 1/4 plus 4 times the cosinus of x. The derivative of 2x to the negative 1/4 would be what? To the negative 5/4. And what's the derivative of 4 cosine of x? Negative 4 times the sine of x. All right, so the next one is dependent on directions. Calculator or no calculator? Multiple choice, not multiple choice. It depends. Slope of the tangent line at a point, calculator can handle that pretty easily. Now, it might not give us the answer the way we want it, in which case we might want to kick over to an analytic approach, because if you have multiple choices that are all in terms of pi, or theta, or a radian measure, or, well, that would be theta, or a radical, basically exact values, but you have a decimal, then there needs to be some sort of adjustment. But I could just do math 8, put in, well, I'll just use x. You can put it in t if you want, but the function 2 plus 3 times the cosine of x, and then pop in the relevant x value, which is pi. Make sure your calculator's in the right mode. I always have to check because the freshmen keep changing it. Should be in radian mode. I looked, but I didn't really look. Always radian mode. And so we get 0. Hey. So you have your answer. Slope of the tangent line is 0. But let's do it anyway, just because. So g prime of t would be, well, the 2 is going to go to 0, right? 3 times the cosine of t has a derivative of what? -3 times the sine of t. So I need g prime of pi. And by hand, it's actually not that bad. It's not bad at all, because we know anywhere on the x-axis, the sine value is going to be equal to 0. So that's 0, pi, 2 pi, any multiple of pi, whole number multiple of pi, integer multiple of pi. Anything on the y-axis, cosine is going to be equal to 0. So just keep that in mind. So calculator by hand, either way. You can also just look at the picture sometimes. If it's, in this case, it should be pretty obvious. So 2 plus 3 cosine of x. I'll do a zoom trig, zoom 7. Yeah, we're looking at pi, so it should be fine. Yeah, so I can do a value, second trace, value, put in the pi, just to get a look at where it is. It's at a turning point. If I were to estimate a tangent line at that location, it would be a horizontal tangent. Horizontal lines have slopes equal to 0. Right? So we can get it that way. But you might question, why on earth would I do it that way if I have a derivative function right here that will not only place it in the location that I want, but also give me the derivative at that location. So that's like the best of all possible worlds. Right? So you get a look at it, you can see that it has a derivative of 0, and also that it is in fact a turning point. Right? So that leads us to number 5. Determine the points where you would have a horizontal tangent if they exist. You might start by looking at the picture. 7x plus sine of x. Window 0 to 2 pi. I'll zoom fit the y min, just so I have a good window. The change of variables seems weird and arbitrary and useless, but we're, like not us, but imagine down the line, like you have me for all of your future math classes. If that is the case, then we would eventually get to some topics where we define our functions in terms of the radius. We define it in terms of arc length, which would be s. We define it in terms of time. We define a function in terms of another function, right? So there is meaning to the change in variables. It just doesn't seem very meaningful right now. So looking at the picture here, it does not appear on this interval that there would be a horizontal tangent. I don't see a clear turning point. So that's a good place to start, because there could be one, and maybe it's just not showing up obviously in the picture. Maybe there's some like micro change in there that's just not noticeable at this level of zoom. G prime of r would be 7 plus cosine of r. If it's going to have a horizontal tangent, it's got to have a derivative equal to 0. Solve for cosine. Cosine of r would be equal to -7. At that point, we would say no solution, because cosine has to be between what and what? -1 and 1. This is outside the domain. The range. So maybe you don't realize that. So you go to take the inverse cosine of the -7, and you get an error domain. Right? So that's your indication there. So the cosine value has a maximum of 1, a minimum of -1. It's never going to get down to a -7, not without having a leading coefficient of 7 or more or less. -7. Right? So no locations in which it has a horizontal tangent. Horizontal tangents are pretty important, extremely important. They're going to come up over and over again. The College Board, me, everyone, we like to ask about horizontal tangents in as many different ways as possible. So there'll be things like determine a location of a relative maximum. So maximum point on the graph, which is implying a turning point. So that's another way of saying it. turning points have horizontal tangents, all right? It might say relative minimum. It might say explicitly horizontal tangent. It might say locations in which the slope is equal to 0. There's a lot of different possibilities, all right? Location in which the graph is unchanging, right? So there are just so many different ways of asking it that you just got to know. And that's kind of a good thing too, because if you're ever in doubt and you know you're dealing with a derivative question, take the derivative, set it equal to 0 and solve. That's probably what the question's asking you to do. I mean, more often than not, you know, so just do it because it's probably right. And then worry about why you did it later.